Hello, everyone. My name is Oskar Halacek. I'm a biophysics professor in the physics department. Thanks for tuning in to our very first online colloquium in the physics department. As many of you know, the pandemic had forced us to suspend our beloved physics colloquia pretty much 2 months ago when we had to cancel Leonard Susskind's Oppenheimer lecture over safety concerns. And today, at the end of the semester, we resurrect our colloquium series with a topic that couldn't fit more, namely, how can physicists and physics approaches be helpful to actually fight or better understand the epidemic? And of course, physicists are not epidemiologists for the most part. They are outsiders, but they bring to the table really a genuine sense for numbers and for how to extract essential features from complex systems and turn them into predictive models. And I think these traits of quantification are really badly needed in times like these, which are often, at least the news, dominated by misinformation and partly deliberate misinterpretation. Also, the colloquium is different in the sense that this work that we're going to showcase from two members of our department is not work accrued over years of work, but it really has been done in the last couple of months. It appears on preprint servers and has not been peer reviewed yet. But nevertheless, these are very serious approaches to make progress and to help essentially in this time of crisis. So let me introduce the first speaker, who is Uros, Professor Uros Seljak from the physics department, who many of you will know. Uros did his bachelor at Ljubljana University and earned his PhD from MIT. He joined the Berkeley physics faculty in 2008 after serving as faculty in Princeton, ICTP Trieste, and University of Zurich. Uros is trained as a theoretical cosmologist, but his recent work has really focused on how to extract fundamental properties of our universe from cosmological observations to answer basic questions such as what mechanism seeded the initial structure of the universe and what is dark energy. His research has a strong interdisciplinary component in developing statistical and data analysis methods for wide applications. And today he will tell us how such approaches, in particular machine learning methods from astrophysics, can also be useful to infer how dangerous the COVID pandemic really is. So without further ado, let me now turn to Uros.
You might mention quickly about questions being asked.
Oh yeah, I forgot that. Yeah, of course we encourage questions, but those should be typed into the chat box, which we then try to collect and ask in 5 minutes.
Okay, thank you, Oskar, for the introduction. So the title of my talk is Time Series Analysis of Italian COVID-19 Excess Mortality Rates. And before I delve into the details of this analysis, let me first tell you a little bit about why we astronomers and physicists care about time series analysis. Here's an example. On the right, I'm showing an example of a time series. On the bottom, of a time series from Kepler data, which observes stars every half an hour. It records a flux. And what you see here is that there's a time series which has some fluctuations, which are due to the stellar variability. And then on top of that, what we're looking for are the planet signatures. All right, so the basic idea is that we try to separate the signals of the stars from the signals of the planets. In this specific paper that we posted a year ago, we actually proposed Gaussian process analysis for the stellar variability component. All right, and I'll explain in a few minutes what the Gaussian process analysis is. But this is a Gaussian process analysis is what we will be applying to the COVID data from Italy. All right, let me move on. I'm gonna tell you what this talk is about. Here, the talk is about estimating the excess mortality in the Italian mortality data that happened this year, in March, mostly in March of 2020, relative to the historical data. So we are not using the official COVID mortality data here. We're just using all of the mortality data that have been given to us by the Italian Stat Institute, ISTAT. And then we're comparing this year's mortality to the historical data to estimate both what the excess is and also to estimate the errors. Now, when we started doing this, which was, I guess, sometimes late March, we thought we were the only ones doing it. Since then, there have been a lot of analysis like this. You can read them actually even in newspapers like New York Times and Economist. But what we're bringing to this analysis is a bit more rigor in the sense of providing also the error bars, and then I'll explain also the interpretation part. Okay, so here's the data. What we are given is the data from essentially January to end of March of this year and the past 5 years. And we're given this for every town in Italy. And not only we're given the mortality data for every town, but also we're given the age information and the sex information. So it's actually quite a rich data set that can be used for a lot of different things. Ask the question, what? So the data is are these observations which we per region, and we take all the Italian regions. Here I'm showing an example of Lombardia, which was actually the most affected region. It is therefore to use the control from the past 5 years to estimate what is called counterfactual. So in other words, there's something that is not real, it's counter to the, compare this to the factual data to estimate the excess. All right, so there are a couple of words that people usually use in this field: controls, treated unit, treatment. Treatment here would be the start of pandemic, which we are somewhat randomly assigning to be the time of the first death in Italy, which is February 20th. Okay, so the simplest prediction would be just to take the mean of the historical data, but this would not be quite correct because as it happens, this year's data, mortality data, are somewhat lower than the mean of the past 5 years. Maybe the flu season was a bit weaker, maybe the winter wasn't as severe. There are many different reasons why there are these fluctuations, yearly fluctuations. So what we're trying to do, therefore, is we want to use this year's information combined with the historic data past February 22nd to kind of give something, minimum variance estimate of what the prediction would have been in the absence of this intervention, the intervention being the pandemic. So we approach this with the Gaussian process. In particular, we do this conditional mean. As I said, you have two sets of information you can use. One is the data before February 22nd, mortality data before February 22nd. So that's this black points up to here. And second, you have historical data from the past 5 years after February 22nd, which are these 5 lines here. We want to combine these two pieces of information in an optimal way. And to do this, we literally just form a Gaussian process description where we say, okay, there's both of these, the data follows a mean, but this is a conditional mean, conditional in the sense of being conditioned on the data before February 22nd. The solution is very simple. This is basically, as I said, conditional mean. This is expression in a Gaussian process. That's all we need to do. And what is nice about Gaussian process analysis is that it also gives us covariance matrix of the prediction. So in other words, it gives us an error bar. There are technical details here. How do we choose the kernel for the Gaussian process? We have chosen the kernel, which is a combination of principal component analysis and a stationary kernel. But those are details that really didn't seem to matter very much for our analysis. Okay, so now that we have established what we're actually doing, so again, what we're doing is we are predicting the counterfactual and we are comparing it to the factual here. So now let's look at the results. We are first validating the counterfactuals on pre-interventions in the sense that we are validating them on the data which we already have. By definition, actually, the Gaussian process does this by definition, so there's actually nothing to validate. Here, we have tried another method, which is called synthetic control method, which is very popular in econometrics. It gives more or less consistent results with our method, but doesn't actually naturally give an error bar. And so I will focus on the Gaussian model predictions in this talk. Okay, so here again, the counterfactual is the green here. The mean, historical mean would be this one here, the magenta. And you see the counterfactual can be a lot lower than the historical mean because this year was a low, low mortality season. And then you see the actual data starting to jump far above the counterfactual after February 22nd. And we see this for many different regions. And so that's what we're going to try to now to estimate what is the excess mortality and how does this compare to the official mortality assigned by COVID. All right, so here's the answer to this. We actually just received today the new update, which we're still analyzing. But as of today, the data is much more complete than it was as of yesterday. So now we actually have completeness in Lombardia and Bergamo, which is almost nearly 100%. In fact, in general, the completeness for northern regions is very high, and we are essentially scaling up the 86%. We're scaling up things, assuming at random, for the remaining 14%. A lot of my analysis will be focused on Lombardia and Bergamo, where we're essentially complete. Now, we still need to extrapolate. So these data only go up to March 28. We still need to extrapolate past March 28. And we have assumed a very conservative assumption, we think, which we're saying, even though this is the excess death, and you see excess death is far above the official COVID deaths. So what we're trying to do here is we're trying to be conservative and trying to extrapolate and say, well, in time, maybe the two catch up, and we're going to extrapolate so that the two are equal on April 11. So, but what you see from this plot, for example, is that on a weekly basis, our counterfactual analysis suggests in Lombardia, for example, a factor of 2 higher mortality than the official COVID mortality assigned by official Italian counts. This is true for Lombardia, true for Emilia-Romagna, for Piemonte, for several of these. I will also focus a lot on Bergamo, which was the hardest hit province in Italy, and I will talk more about this one, but you can again see at least a factor of 2 higher mortality. Okay, so the assumption is, we are of course making the assumption that this excess mortality is due to COVID-19. We think this is the most reasonable assumption, but there are alternative options that one can discuss, which we discussed in the paper. We think they're less likely, but it is an assumption. Let's see. All right. So here are now the results for different regions in Italy. Not all the regions have a factor of 2 overestimation. Some have more like 50%. But some of the hardest hit regions, like Lombardia, official COVID deaths is, let's say 12,000. Our estimate is more like 22,000. So almost a factor of 2 higher. So now if we add up all of these data points together, we find roughly 1.6 times higher mortality than official numbers. So official numbers are as of today are roughly 27,000. And maybe this estimate is more like 42, 43,000. We're still analyzing this because, as I said, we actually just got the data today. So in terms of what the total number of mortality we're estimating in Italy, I said it's probably about 40,000, but we're still getting to the numbers. Okay, now what is interesting about this data has amazing statistics, right? A lot of people died in Italy. And so we can, and moreover, we also have information as a function of age. And so here we have split now this information as a function of age, and we have estimated the mortality as a function of age. And I'm showing again 2 of the most hard hit region and province. So the hardest hit region was Lombardia, hardest hit province was Bergamo. And what you can see, first of all, is that at low ages, below 50, there's not that much difference between the official COVID deaths and our estimates. In other words, most of the people that died below age of 50 have been also correctly officially counted. But this actually is less and less true as we go to higher and higher age populations until we hit a population above 90 where official count might be at 1,000, and the true count might be 4,000 for the Lombardia region, for example. So a huge excess over official counts. There is the hypothesis that basically these are old people that were dying at homes or in retirement homes. They were never tested for COVID, especially during the crunch of the crisis in Italy, where they did not have enough tests, and also the hospitals were overrun. And so basically these are people that were just never tested. So that's the hypothesis, which kind of is confirmed by anecdotal evidence from the statements from the hardest hit regions in Italy. But what is interesting here is that we are seeing a very large ratio in terms of very steep function of the mortality as a function of age. And I'll show that on the next plot. But before I get to that, I need to define a few things. I want to define various fatality rates. Population fatality rate is essentially number of deaths divided by total population. So this is a very robust number that we can just get out of the total number of deaths. Now, infection fatality rate is number of deaths due to infection divided by number of infected people, which is population times infection ratio. I'm going to shorten this as IR, infection ratio. And so IFR is bounded from below by PFR, because infection ratio cannot be more than 1. So that already gives us an estimate from the total fatality rate of Bergamo, which was the hardest hit province. 6,000 people died in Bergamo. Population is 1.1 million. So that already gives you a lower bound on the infection fatality rate of 0.55%. Right there. It's a lower bound because we're assuming 100% infection rate. There's a better way, or maybe tighter lower bound, which we can get by getting information from test positive rate. In other words, what fraction of people have tested positive, which for Lombardia, for example, is 27%. Unfortunately, we don't have this information for Bergamo province, so we could not use this one. But if you take population fatality rate and divide by this upper bound on infection rate, which we are estimating from this test positive rate, then we get about 0.8% lower bound on infection fatality rate for Lombardia. So that's a slightly tighter lower bound than this 0.55% for Bergamo. Okay, so these are lower bounds on the fatality rates, infection fatality rates. It's harder to actually get an upper bound on this. This data cannot really give you an upper bound. The only way to get some estimate of an upper bound is to have some independent estimate of infection fatality rates. I'll talk more about the Diamond Princess data and how we get this estimate. But roughly speaking, from Diamond Princess data, we get an upper bound of roughly 1.6%. So in other words, for Lombardia, we would say the fatality rates are between 0.8 and 1.6%. All right. Now let's talk about infection fatality rate as a function of age. Here I'm showing the population fatality rate for different provinces and for Bergamo. And here I'm showing this infection fatality rate where essentially I divide this number by our best estimate of infection rate, which I'll talk about on the next slide. But you see basically all of these numbers, they come closer together. But we could also just focus on the population fatality rate for Bergamo. And you will notice very, very steep dependence on the age. For example, if you are below 50 in the age bracket 40 to 49, the probability of dying from if you get infected is 0.02%. On the other hand, if you're above 90, then the probability of dying is 10%. So roughly speaking, the ratio between these two is 500. So it's a huge, very steep dependence. And it's much steeper actually than what the current models are actually using. For example, the most popular models are Verity et al. Models from Imperial College London, and they're less steep than what the data are actually telling us that they should be. Under the assumption, of course, that the infection rate is constant across the ages, which is an assumption that everybody makes, including the Verity et al. But if you make this assumption, then this data are just literally telling you what is the fraction of what is the infection fatality rate as a function of age. and it's very, very steep. And again, partially this is explained by the fact that some fraction of people were just not counted in the mortality, especially the older people. Okay, so what can we say about infection ratio? So here we try to bring in some external information about infection fatality rate. It's very hard to do this because there's very little information on this. The best shot we have is from Princess Diamond, which was kind of a complete and unbiased sample because everybody got tested. There were 330 infections, 11 people died above the age of 70. And so roughly speaking, for above the age of 70, infection fatality rate is 3%. If we then do the age adjustment to, let's say, Lombardia, we can say Lombardia population fatality rate is 1% in this age, or actually slightly less than that. And so then if we take the ratio of these two, we get infection ratio, which is about 23%. Remember, I said the upper limit to infection ratio was about 27% from the test population, test fraction, test positivity fraction. Okay, so infection rates vary strongly across the regions, not surprisingly in Italy, and that's the same is true also for US. All right, so finally, what can we say about case fatality ratio? Case fatality ratio is number of fatalities divided by number of positive tests. So it's bounded from below by infection fatality ratio, but often it is much, much higher than this. This number varies drastically across the countries, and this is actually the number that people often hear most, but it's probably the least useful number because it is so affected by the number of tests performed. For example, let's take a Lombardia. Lombardia has tested about 2% of the population. 30% of that population has tested positive, so 0.7% has tested positive. But as I mentioned before, infection rate for Lombardia is probably 23%. That's our estimate. So this number is 35 times higher than this number. So in other words, the tests have only been probing the tip of the iceberg in highly infected regions like Lombardia. So one can, however, ask the question, are low CFRs, case fatality rates, a problem for our predictions? For example, Iceland has a very low case fatality rate, only 10 deaths out of 1,800 infections. Now, this number has a large Poisson error, and so it translates into infection fatality rate upper bound of 0.3 to 1.2%. Okay, so one could argue that Iceland does set some kind of upper limit as well on the infection fatality rate. Now, Iceland has a younger population, and we actually predict that the lower bound for Iceland should be 0.5% rather than 0.8% in Italy. So there's another, there are a couple of countries actually that have very low case fatality ratios. For example, Singapore is 0.1%. And the question is this in conflict? Now, experts believe that this is not in conflict with these predictions because most infections happen among the immigrant population, which therefore do not then infect the older population of people. And so it's likely that infection ratios in places like Singapore are actually age dependent. And that's an important thing to keep in mind, that all of these assumptions of these epidemiological models, which assume everybody is infected the same rate, regardless of age, this may not be true, and maybe Singapore is an explicit example of this not being the case. Okay, so now let's in the last few minutes, let me talk a little bit about US. We are making a very simple a model prediction, which is if you want to translate these fatality rates to other regions, you can just use roughly the yearly mortality rate. In Italy, yearly mortality rate is 1.1%, and that's very similar to the IFRs I was quoting. But in New York City, it's 0.6%. And so we are predicting a lower bound and a lower mean than Italy for New York City. Okay, now we know in New York City, actually, the population fatality rate has already reached 0.15%. So if we take this ratio of these two numbers, then we predict that 25% of population is infected with a large error because we actually have quite large uncertainties on this. But again, if you compare this to the number of people that have been tested positive, this number is much higher than this number. A ratio is about 15 or so. And so again, in New York City, also the people that have been tested are only at the tip of the iceberg. There's one more thing that this model predicts, which is that we can explain why the age distribution of New York City deaths is tilted towards the younger population than in Italy. The reason for this is that the same is true in just the normal mortality rates. In other words, if you go into the tables and ask what fraction of people in New York City that die per year are under age of 65, the answer is 26%. And that is actually very similar to the COVID death fraction. The corresponding number in Italy is 10%. And again, in Italy also, the corresponding numbers of the yearly mortality rates and the COVID deaths, the fractional deaths as a function of age trace each other. All right, so basically, COVID is, mortality is tracking overall mortality. So one can say that COVID is basically, killing the weakest segment of population. Okay, so again, if you want to have a quick estimate, what is the chance of you dying if you get infected, is the same as you dying over the next 12 months. That's a quick way of estimating this. Okay, there's been a lot of talk about this excess mortality here in US now. Here is a plot that our postdoc George Stein made. But the basic message from this from this plot is New York City includes probable deaths, which has increased the mortality by 50%. And once you account for that, then that more or less accounts for all of the deaths. So in other words, if you account for these probable deaths, then you're probably doing a good job. And this mortality analysis confirms this. Finally, what about California? California, we have also a younger population than Italy. So we predict, again, 0.6% on the mean, 0.5% lower bound. We can compare these numbers to, for example, Santa Clara, 120 deaths, 2 million population roughly. So that gives a rough infection rate of about 1%. Now, again, I'm assuming that infection fatality rate is lower bound is 0.5% and the mean is 0.6% and maybe upper bound is 1%. This is inconsistent with the recent seropositivity study of Ben David et al., which were claiming 0.1 to 0.2%. But there have been many issues with their statistical analysis that have been discussed in the literature. I won't go into details. I'll just mention two of these things. First of all, their raw seropositivity rate, infection rate is 1.5%, which is not that far from this prediction. And second, these seropositivity tests still have a large false positive rate, which one would have to subtract out. And it's quite possible, actually, that could be as high as 1.5%. So this Santa Clara study is certainly inconclusive. Now, LA study is more interesting because LA is more infected. In fact, the number of deaths, we can tell this just from the number of deaths there. It's a factor of 2 higher per million per population than Santa Clara. And so by this prediction, we would therefore predict 2.5% infection rate in LA County, which is not that inconsistent with the recent seropositivity study, I should say by some of the same people. Which is roughly 2.8 to 5.6%, again, without corrections for the false positive rate and stuff like that, which is still very controversial. So overall, all the data are consistent with California being infected roughly at 1 to 2% rate at the moment, which is much, much lower than, let's say, New York City, which is probably at the level of 20%. And so far, there's no evidence of any deviation from the normal infection fatality rate of roughly 0.6%. Okay, this is my next to last slide. I'll just mention where we're going next. We want to do now epidemiological models as a function of age, because we want to improve the epidemiological models, and we want to do mortality, time to death mortality distribution as a function of age. We think that nobody has looked at this. We think we have data that it's worth looking at this because we have such a high mortality rates that we think maybe we can do something useful about this. All right, so that's one thing we think we can do, and we already started. I'm just showing here a very quick preliminary results of basically data mortality as a function of age, and then epidemiological model predictions, function of age. I mean, the basic idea is just to see that the two are kind of comparable. And then also we would like to verify further this hypothesis that infection fatality rate is tracing the yearly mortality rate as a function of age as well. And so we would like to have mortality data as a function of age, sex, race from US, which we do not have at the moment. And so it would be nice to have that. And then finally, of course, the ultimate goal is, can we refine the epidemiological models to track the outbreaks better? And in fact, maybe one message here is in machine learning language, mortality is the actual loss function we want to minimize, right? And so it makes sense to focus on mortality and makes sense to see what measures will actually minimize the mortality. But one cannot do this unless one has very precise mortality data, infection mortality data as a function of age, as a function of time, and fold that into the models. And that kind of information is not available yet at the moment as a function of age, sex, and things like that. And that's what we are trying to improve with the future data. Anyway, so here's my summary, and I'll stop here and I take the questions.
Thanks a lot, Uros, for a really illuminating talk. We have tons of questions, and we probably cannot go through all of them, but I can relay them to you later on. But let me start at the top. The first question I see here, is it possible to distinguish the cause of the excess mortality? For example, instead of a shortage of tests in retirement homes, could it be that there are excess non-COVID deaths because of hospitals being overrun or other causes?
Yes, so we have a little bit to say about this, but not that much. But basically, we see the largest excess happening in the first few weeks of the pandemic, when the hospitals may not have actually been overrun. So it's not clear that this hypothesis that the hospitals have been overrun is actually valid. But I'm getting into the realm of speculation, which I don't really want to do. So if somebody wants to believe that this is happening, then the best answer is, well, yeah, let's check it in other places. Now, of course, maybe other places have also been overrun the same way. But we see this excess mortality at the level of 50% everywhere, including, as I said, New York City, where they have added the probable deaths. So it seems at this point very reasonable that 50% of the population has not been tested, but has died from COVID.
All right. The second question is, do you see a steeper decline in deaths after the peak in areas that had high infection rates, as you might expect with partial herd immunity?
Right. One thing I forgot to mention, Bergamo province is the only one that may have reached the herd immunity. And we definitely do see very steep, well, let's look at this one here. We start seeing the decline, but as I said, our data only go up to March 28. We are just past the peak in Bergamo and maybe just at the peak for Lombardia, so it's kind of hard to tell. We do have actually data which we received today that take us for next 2 weeks, and it will be interesting to see what happens there. Yes, hopefully, maybe today or tomorrow I'll be able to answer that question, but not right now.
All right. Is there anything you can say about the dependence of the testing rate on age and how that might affect these fatality rate models?
The testing rate, our predictions do not depend on the testing rate at all. So I probably don't understand.
Maybe the case fatality rate, right? Cases are tested, confirmed cases. So that,
yeah. Which is why I didn't focus so much on case fatality rates. So, case fatality rate is probably a useless number.
It's not of importance. Yeah. Okay, maybe last question, but that's probably a realm of speculation. Could the age dependence of the infection rate be due to social factors? Hard to say.
Age dependence of the infection rate.
Yeah, that's.
Okay. So on the infection rate, we have been assuming that infection rate is age independent in this analysis. That seems a reasonable assumption, especially for places like Bergamo, which probably have reached herd immunity, and infection rate is, our estimate is 50 to 100%. So it seems reasonable that just everybody got infected there. I was mentioning, however, that infection rates might be age dependent, and there's maybe some evidence for that from Singapore data, which would nominally otherwise violate our infection fatality rates. Because if case fatality rate has to be higher than infection fatality rate, but case fatality rate in Singapore is 0.1%. So how can that be? Either they're dying, either infection fatality rate actually is different there, or it's the infection rate that is different. In other words, most of the young working population is infected and most of the older population is not infected. So that is an example of what this person is asking, right? There is some evidence that this is happening. It's probably happening. It's probably a lot more likely that this is happening when infection rates are very low than when infection rates are very high. So I would probably argue that for Bergamo, assumption that everybody's infected at the same rate is more reasonable than when infection rates are 40%.
All right, thanks again, Uros. Let me now turn to our second speaker. Vir, could you perhaps share your screen? First, Uros perhaps needs to unshare his. Great. So our second speaker is Vir Bulchandani, who is a PhD student, current PhD student in the department. Vir was an undergrad at Cambridge and is currently completing his thesis with Joel Moore on emergent hydrodynamics and quantum condensed matter. He will be moving to a fellowship position at the Princeton Center for Theoretical Sciences in the fall. Vir will talk about app-based contact tracing, which combined with swift quarantine measures holds great promise for stopping infection chains early. But even if you could realize the approach, how many people would really need to participate? And so I think Vir has developed a minimal model to get an answer for that question. Vir, please take it away.
Hi, everyone, and thanks for the opportunity to speak here today. I'm going to be talking about digital herd immunity and COVID-19. I'd like to start by thanking my collaborators, Soumya Shivam and Sanjay Mungalia, graduate students at Princeton, as well as Professor Shivaji Sondi, a condensed matter theorist who inspired all of us to start thinking about this topic. We benefited a lot from discussions with Shoiba Chakravarti, physicist and policy expert, as well as Professor Vijay Raghavan, principal science advisor to the government of India, and finally Brian Grenfell, an epidemiologist at Princeton. Okay, so our goal was to quantify the effectiveness of app-based contact tracing. And the reason, there were two main reasons behind this. Firstly, lockdowns are economically ruinous. Is there a smart solution that might get around this unpleasant situation we all find ourselves in? And secondly, India's particular challenges of scale provided a particular impetus because physically testing a sizable fraction of 1 billion people is clearly infeasible, and app-based approaches might be readily scalable. So we kind of fixed on this as a practical option to look into further, but when we tried to consult the literature, we found that actually the values and the meaning of contact tracing compliance thresholds were a little unclear. And although mathematical epidemiologists had studied the problem before, most notably in the early 2000s, there was actually, in the specific regime of app-based tracing for COVID, there actually were not any clear analytical results. So we went in trying to come up with a minimal model that would give a value for this compliance threshold and also some sense of where it came from. So that was the goal. I'm going to start by just introducing some basic epidemiological notions in a physics kind of language. So first, this It's often discussed herd immunity. Well, we can understand it in a cartoon of a disease where each infected individual goes on to infect a fixed number, R0 on average. And then the question you can ask is, how many of the population need to be vaccinated to prevent further spread? Well, if a fraction V is vaccinated, a fraction 1 minus V is susceptible. So your effective reproduction number is just R0 times 1 minus V. So let's say you have your population and then an infected seed comes along, well, they're going to infect R people who go on to infect R squared and so on. And then summing the geometric series, it either diverges on average, the epidemic spreads, or it converges. And the threshold at which it converges is what's called herd immunity. So for example, for R0 of 3, it's around 2/3. And this is a controversial policy that was actually pursued initially in the UK. The idea there was that letting the disease spread would allow the population to develop endemic herd immunity, but the problems are twofold. The collateral damage is huge, and typically in the disease dynamics, you massively overshoot. So you might even get up to 90% infections before the dynamics stop. So this is one motivation for thinking of smarter approaches. How do you connect this to statistical mechanics? Well, let's take R0 of 3 for concreteness and draw this branching process explicitly. You can think of it as an epidemic phase if an initial infection propagates to infinity on average and an immune phase otherwise. And this actually has a classic interpretation in statistical physics, which is it's the embedded branching process of what's called site percolation on the beta lattice, where you have a lattice whose coordination number is just R0 plus 1. And so one thing to bear in mind for the rest of the talk is maybe this dictionary between epidemiology, statistical physics, and math, where you have epidemic spread is equivalent to a non-zero percolation probability is equivalent to uncertain extinction of your branching process. Now, of course, this is an idealization. Two major sources of stochasticity we didn't include, which professional epidemiologists tend to include, are variance in time periods and variance in the degree per node. So for example, super spreader events, you can have a node which has a much higher number of offspring. But I will say that despite not including these refinements, I think our model captures the essence of what's going on, and the thresholds we obtained are actually in quantitative agreement with what analyses taking all of these things into account predict. So with that qualifier, let me introduce some stylized facts about COVID that we'll need to understand contact tracing and how it works. So broadly speaking, it seems that you have two types of infection, symptomatic and asymptomatic. Now, the symptomatic ones are characterized by three time periods of interest: an incubation period lasting 5 to 6 days, a pre-symptomatic contagious period lasting maybe 1 to 3 days, followed by a symptomatic contagious period of 14 days or more. In contrast, an asymptomatic infection has a similar latent period, but never shows symptoms, despite being infectious. So you can think of it as what we call this omega period, lasting for the entirety of infection duration. The other facts we'll need are that the data before interventions is consistent with a basic reproduction number of around 3 across the board. And finally, we're going to estimate the fraction of asymptomatic spreaders as around 1/2. So in our view, this is a reasonable estimate. It seems that data is even consistent with a higher fraction of asymptomatic transmission. And this is really, Uros mentioned the difficulties of gathering data in this problem. From our point of view, one major source of dark matter is this asymptomatic rate, which doesn't seem to be well understood. But anyway, 50% seems reasonable, so we'll go from there. So given these simple parameters, how does contact tracing work? Well, if you only had symptomatic cases, it would actually work in principle. So, because suppose you have patient 0 in a given population. They exhibit symptoms on around day 7 of infection, and they go to the hospital. One can then identify their contacts on days 4 to 6, that pre-symptomatic contagious period, test and quarantine rapidly, and then you're done, because these new infections have not yet had time to become contagious. In the language of the previous slide, this omega period is smaller than the latent period, which is why this works. And in fact, some diseases are controllable in this way. For example, SARS and smallpox, but not COVID. And there are two difficulties that arise in general. Firstly, the rate of asymptomatic transmission can be non-zero, or indeed appreciably large. And also the fraction of people whose contacts can be traced is never perfect. So the sharp question we wanted to try to address is it still possible to achieve epidemic control, even if you have a large number of cases you may not know about, and not everyone is running the app? So before I get into the details, let me just walk through contact tracing with how we detect asymptomatic cases. With contact tracing, you only detect them once they give rise to symptomatic individuals. So you have to trace contacts back in time and then forward in time to find the other asymptomatic cases they gave rise to. The other option you have is random testing. But the problem with random testing is it's not scalable. So a bottom line is the only scalable solution for detecting a large number of asymptomatic cases is a combination of tracing and testing, it seems to us at the moment. Okay, so our goal for the rest of the talk will be to understand the phase diagram of epidemic spread with these two tuning parameters, this asymptomatic rate theta and this app ownership or contact network rate phi. And we can envisage a tentative phase diagram like the one shown, where if not enough people are using the app or you have too many asymptomatic spreaders, you're in an epidemic phase, otherwise you're in an immune phase. And I'm now going to back this up with some numerical and analytical results. So just to describe the branching process model, it has these independent probabilities theta and phi that you just met. We also assume different reproduction numbers for symptomatic and asymptomatic cases. The reason is that a symptomatic individual is only expected to infect during their pre-symptomatic contagious period. Given the current climate, it's reasonable to assume that they're isolated once they show symptoms. And so in terms of these four inputs, we want to understand when the effective reproduction number falls below 1, when this geometric series converges and you don't have population. So before I show the numerics, I want to just summarize how contact tracing works in our model. So in this example, figure 1a shows an asymptomatic source infection who's on the contact network. In one generation of disease spread, they generate 3 further infections, who will then go on to infect one step further. So figure 1b shows when 2 generations have elapsed, but now the symptomatic individual on the contact network with the red exclamation marks has shown symptoms. So that sends out an alert on the contact network and to everyone connected to that node with the arrows. And then figure C shows the tracing and isolation of this network connected cluster. So this is how contact tracing, app-based contact tracing would work in practice. You find these, digitally find these network connected clusters and trace and isolate them. So we wrote a code which did exactly this, write down where you work with the adjacency matrix of the contact network and prune connected clusters as they arise, as you detect them. And we found a positive answer to the question posed earlier, namely that for any rate of asymptomatic and pre-symptomatic transmission, epidemic control is achievable in principle if enough people are on the network and tracing and testing are working perfectly. So that was our main result, and we have quantitative estimates that I'll come back to below. The details on these plots are analytical predictions, and since I have a physics audience, I'll just briefly summarize how we got those. So I'll start with a critical point along the line theta equals 0, when transmission is purely symptomatic. And this is relatively simple because you only have two types of nodes. You can either be on the network or off it. Now, a standard technique in percolation theory is to study the probability of formation of an infinite cluster. And the nice thing about these simple kind of Cayley trees or beta lattices that arise in our branching process is you can get this recursively. So you can write down a recursion relation for the percolation probability, find the exact critical point on that line. Pushing this type of calculation further, you can get critical exponents. And although it's more complicated than mean field site percolation, we found the transition lies in the same universality class. So this was a relatively simple case. Things get much more interesting when everyone is on the network, because this is when you start having effects that are non-local in time. You can start tracing back and finding infections that way. So the figure shows how varying the contact tracing depth works. So the further back you can go in time, the more asymptomatic infections you can detect. And this causes the critical point to actually move as you increase the tracing depth. And equation 6 is already quite non-trivial compared to simple percolation models. We found actually that the critical behavior is also pretty unconventional. While for any finite tracing depth, you have a mean field exponent, as you go further and further down on the network, you actually get a discontinuous phase transition. So I'm just flashing a slide here with the calculations. The bottom line is that the two endpoints of this critical line have completely different critical behavior because of the effectiveness of recursive contact tracing. So trying to understand how it interpolates between mean field percolation and discontinuous percolation is still work in progress. One thing we have been able to do is get the location of the critical line to high precision. So you can essentially sum these contact tracing processes by hand and get fairly accurate predictions, as you can see. Those are the red dashed lines. So that's all I wanted to say about the statistical physics of the model. Now for practicalities. So for an R0 of 2, we found a required take-up threshold of between 50 and 75%, depending on the rate of asymptomatic transmission. And these the estimates range from low to reasonably high, and if R0 equals 3, this range jumps from 75 to 95%. So these are the numbers we passed on to policy people. They're consistent actually with the more detailed epidemiological modeling I mentioned. So there was this paper by Ferretti et al. In Science, which kind of kicked off this whole discussion. And they had a number of 60%, given a relatively low theta of around 0.2, which they've since revised upwards to 80%. And we suspect that's because, like us, they've become more pessimistic about this rate of asymptomatic spreading. So the bottom line is, for realistic parameter values, it seems like this app ownership threshold for this digital herd immunity phase is pretty high. And so we've come around to the view that it should probably be used in combination with other interventions to try and basically lower the threshold for endemic herd immunity. The idea is that all of these immunities are emergent effects in some sense, and you can bring down the threshold successively by introducing further interventions to bring that effective R lower and lower. So our original motivation was India, and given these thresholds, you immediately run into the issue that actually smartphone ownership in India is only 40%. So it seems far from feasible, even in principle. But since 90% of people actually own some kind of phone, you can imagine, say, cell tower triangulation to make up the difference. Now, of course, this is more coarse-grained. It's more like if you're in the dilute limit and there are very few infections, you can imagine sending out a notification to an entire neighborhood. But actually, given how few cases there appear to be in India at the moment, this might be feasible. We're in discussions with people there about how to make this idea work. Now, the most glaring issue in India and everywhere is privacy concerns. And we don't have a good answer on this. I mean, many people are working on trying to make this kind of thing robust to potential threats. We feel that open sourcing the code should be a minimal requirement, but it seems like very few of the countries running the apps at the moment have done this. So, yeah. Don't have anything more to say on that. But one thing we decided to do based on this work was to quantify what's the required rate of testing, assuming perfect tracing. So one thing which has been discussed quite a lot recently is how many tests are needed in the US, for example. And actually the estimates vary wildly depending on what you're trying to do. So if you want to contain an epidemic with random testing, economist Paul Romer did some analysis suggesting that you need to test 10% of the population every day. So that's 30 million tests per day, which is clearly infeasible with present capacity. On the other hand, physicist Marcus Müller and some collaborators looked at how many you need to test just to monitor the growth rates at a statistically significant level in a small country. And they found around 15,000 per day was enough. Scaling up an order of magnitude to the US gives you 150,000 per day. But this involves no prevention. So this is just monitoring. And then finally, the most realistic attempt was from the Harvard Global Health Institute, arguing for around 500,000 tests per day in combination with contact tracing. Now, the problem with this analysis is it didn't really account for asymptomatic spreading, and it didn't really take into account that this could be quite high. So we decided to redo their analysis using our branching process intuition. And we found that the effectiveness of testing actually depends on the R0 as well as the rate of asymptomatic spreading. The bottom line is that to actually catch asymptomatic cases through tracing, you have to do extra tests. And when you take this into account, an estimate like 500,000 becomes revised upwards to more like 1.5 million. So we sent them our modeling and have been discussing further. But the point is that tracing and testing in isolation are probably useless. In combination, they might be very effective. So with that, I'd like to finish, and thank you very much for listening.
Thank you, Veer, for a really very, very clear talk. This is very, very cool work. At the moment, I don't see outside questions, so let me start out with a question. So in the tree, the basic branching process that you studied, there are no correlations between the people that you meet, right? You essentially draw the people from from the whole world, right, without assuming any correlations. But in fact, we have a community with which we interact. We localized in space. So adding those correlations in, how would that change predictions of your model? Do you have a sense?
So that's not something, it's definitely on our to-do list. We haven't had time to do it yet. I will say, so in principle, it's as you described. For the simulations, one actually has to take a finite graph, and then there's some selecting without replacement, which is a kind of finite size effect. But we haven't looked at realistic networks yet. There has been work on the early 2000s for how network structure affects the contact tracing threshold. So people have thought about it, but we don't have a good sense of that.
So isn't it just qualitatively, do you expect maybe these correlations to work in the direction that it makes it maybe a bit easier, in fact, to trace down, let's say, a cluster of infected, because people tend to meet each other?
That could well be the case. I mean, in a sense, what we're describing is like the early time behavior of an epidemic in a big city. Of course, in a community, you could expect to be able to control things better. But I don't have a more detailed answer than that right now.
Great, thank you. Uros has a question. What is evidence for 70% asymptomatic rate? Diamond Princess and Town of Wu suggest 50%.
Okay, 50, yeah. So we're also inclined towards 50%. I think Iceland is consistent with that too. The 70% was more trying to understand this antibody testing stuff out of New York. We don't really understand what's going on there, whether that reflects some large number of asymptomatic cases or these cases are simply non-infectious. So that's where the higher number came from.
I don't have any extra questions, so maybe just a meta question. I mean, you're a condensed matter PhD student, so how did you get into this project in the first place? How did you get inside it? I think it's an inspiring piece of work, so maybe you can tell about that a little bit.
Well, it's funny. I was this whole lockdown kicked off, and I was feeling pretty powerless, and like my work was theoretical and irrelevant. And then Shivaji approached a group of us asking if we wanted to do some epidemic modeling for India. So we started off with working with this code from Johns Hopkins. It was this full agent-based model, and we rapidly realized that maybe this detailed stuff is best left to epidemiologists. So yes, what can we say that's actually useful? And after about 2 weeks, settled on this contact tracing network as maybe something where we could say something new and meaningful. So that was how we got involved in it.
All right, that's really interesting. So on that note, maybe other people in the physics department at Berkeley get ideas as well of what to do, what things to work on. Please exchange ideas. We'll find a way to establish a channel, I think, in the future if there's enough interest. But for now, I think for today we should end the colloquium. And thanks everybody for tuning in. By the way, this is going to be recorded and we'll put it on the net as well.
Thank you.
So bye everyone.
Now that it's just a small group. Thanks very much. I think that was very useful for the department, and I certainly learned a lot. So I appreciate your doing
Thanks, Joel.
And Bernard Sedule just message that he wants to start a small group, or that, well, he doesn't say he wants to start it. He says maybe there should be a small group in the physics department for these things. So I'll let you all decide on that. Anyway, bye for now.